Leopard spots of Mars, humanity's closest encounter with extraterrestrial life, a comprehensive scientific journey prologue. The question that defines us on a clear night. When you look up at the reddish point of light we call Mars, you're staring at humanity's greatest mystery. For thousands of years, we've wondered, are we alone? The ancient Greeks told stories of gods living on Mount Olympus. The Romans named planets after deities. In 1877, Italian astronomer Giovanni Schiaparelli reported seeing canali on Mars channels that were mistranslated into English as canals, sparking decades of speculation about Martian civilizations building vast waterways across their dying planet. We now know those canals were optical illusions, tricks of light and telescope limitations, combined with the human brain's tendency to see patterns where none exist. But the fundamental question remained, does life exist beyond Earth? That question has driven humanity to achieve the impossible. We've sent robots to distant worlds, built telescopes that can peer billions of light years into space, and developed technologies that our ancestors would have deemed magical. And in July 2024, on a dusty plain inside an ancient Martian crater, a six-wheeled robot made a discovery that brought us closer than ever before to answering that eternal question. This is the story of that discovery, the leopard spots of Mars, and what it means for humanity's place in the universe. Part I. The Road to Jezero. Chapter 1. Why Mars? Mars has captivated human imagination since ancient times. The blood-red planet, named after the Roman god of war, has always seemed like the most Earth-like world in our solar system. It's the fourth planet from the Sun, sitting just beyond Earth in the habitable zone, that Goldilocks region where temperatures might allow liquid water to exist. But Mars today is a frozen desert. Its atmosphere is 95% carbon dioxide, and just 1% as thick as Earth's. The average temperature is -80 degrees Fahrenheit, -60 Celsius. Intense radiation from the sun bombards the surface, unfiltered by any protective ozone layer. No human could survive there without a spacesuit. Most microbes from Earth would die within minutes. Yet, scientists have compelling reasons to believe Mars wasn't always this way. The evidence from orbit since the 1960s, spacecraft orbiting Mars, have revealed something extraordinary. The planet's surface is covered with features that could only have been carved by flowing water. There are ancient river valleys, dried-up lake beds, deltas where rivers once emptied into vast bodies of water, and minerals that form only in the presence of water. The most striking evidence comes from the northern hemisphere, where orbital imagery reveals what appears to be an ancient ocean shoreline. Scientists estimate that billions of years ago, Mars may have had enough water to cover its entire surface to a depth of about 450 feet, 137 meters. If concentrated in one place, this would have created an ocean covering much of the northern hemisphere, potentially as deep as 1 mile, 1.6 kilometers in some places. The Mars that was about 3.8 to 3.5 billion years ago. During a period called the Noachian Epoch, Mars was a very different world. It had a thick atmosphere that created enough air pressure for liquid water to exist. On the surface, a global magnetic field that protected it from solar radiation, rivers, lakes, and possibly oceans, rain and snow, a water cycle similar to Earth's temperatures, warm enough to support liquid water for extended periods. Conditions that, on Earth, would have been perfect for life to emerge. Then, something catastrophic happened. The Great Dying Mars is smaller than Earth, about half our diameter, and only 11% of our mass. This seemingly minor difference had profound consequences. A smaller planet has less internal heat, and that heat is what drives geological activity. Earth's molten core generates our magnetic field. which acts like an invisible shield against the solar wind stream of charged particles constantly flowing from the Sun. About 3.5 billion years ago, Mars's core cooled enough that its magnetic field collapsed. Without that protection, the solar wind began stripping away Mars's atmosphere, molecule by molecule. As the atmosphere thinned, surface pressure dropped. Water could no longer remain liquid. It either froze or evaporated into space. The greenhouse gases that had kept Mars warm dissipated. Temperatures plummeted. Over hundreds of millions of years, Mars transformed from a potentially habitable world into the frozen desert we see today. The astrobiological imperative, but here's the crucial point. Life on Earth emerged remarkably quickly. The oldest confirmed fossils of microorganisms date back about 3.5 billion years, just a few 100 million years after Earth's surface cooled enough to support life. Some evidence suggests life may have emerged even earlier, perhaps 4 billion years ago. If life can emerge that quickly within a few 100 million years of suitable conditions, then it might have emerged on Mars during its wet, warm period. And if it did, there's a chance we can find evidence of it. That's why we keep going back to Mars. That's why, in July 2020, NASA launched the Perseverance rover with a clear mission: find evidence of ancient microbial life on Mars. Chapter 2, The Perseverance Mission, the Mars 2020 mission. Carrying the Perseverance rover and Ingenuity helicopter, launched from Cape Canaveral on July 30, 2020, atop a United Launch Alliance Atlas V rocket. After a 7-month journey covering 293 million miles, 472 million kilometers, Perseverance executed a harrowing landing sequence on February 18, 2021. 7 minutes of terror. Mars landings are notoriously difficult. The planet's thin atmosphere makes it hard to slow down, but thick enough to create heat during descent. NASA engineers call the landing sequence 7 minutes of terror, the time from atmospheric entry to touchdown, during which the spacecraft must autonomously execute a complex series of maneuvers. At 2:55 p.m. EST, 7:55 p.m. GMT, Perseverance hit the top of Mars's atmosphere traveling at 12,100 miles per hour. 19,500 kilometers per hour. A heat shield protected the spacecraft as atmospheric friction slowed it down, generating temperatures up to 370 degrees Fahrenheit, 1300 grados. At about 7 miles 11 kilometers above the surface, a supersonic parachute deployed, the largest parachute ever sent to another planet, spanning 70.5 feet, 21.5 meters in diameter. But even the massive parachute couldn't slow Perseverance enough for a safe landing. At about 1.3 miles, 2.1 kilometers up, the heat shield separated and fell away. At 0.4 miles, 0.6 kilometers, the parachute and back shell separated, and Perseverance's descent stage, essentially a rocket-powered crane, took over. 8 retrorockets fired, bringing the descending spacecraft to a hover. Then, in a maneuver called the Sky Crane, the descent stage lowered Perseverance on 3 21-foot 6.4-meter cables. When the rover's wheels touched down in Jezero Crater, pyrotechnic cutters severed the cables, and the descent stage flew off to crash land a safe distance away. Mission control at NASA's Jet Propulsion Laboratory in Pasadena, California, erupted in cheers. Perseverance had survived the landing. Now the real mission could begin. Choosing Jezero Crater, the landing site wasn't chosen arbitrarily. After years of debate and analysis, scientists selected Jezero Crater for compelling reasons. Jezero is a 28-mile-wide, 45-kilometer-wide impact crater in Mars's northern hemisphere. About 3.5 billion years ago, an asteroid slammed into Mars, excavating the crater. Then, over millions of years, water flowing from the surrounding highlands filled the crater, creating a lake roughly the size of Lake Tahoe in California. A river flowed through a breach in the crater's western rim, carrying sediments that accumulated at the delta, that fan-shaped deposit, where a river meets a larger body of water. Orbital images show this ancient delta remarkably well preserved, its layers visible from space. Deltas are crucial for astrobiology. On Earth, river deltas are excellent at preserving organic material and fossils. The fine-grained sediments that accumulate in deltas can entomb and protect ancient microorganisms for billions of years. If life ever existed in Jezero's lake, the delta would be one of the best places to look for evidence. But Jezero offered another advantage: diversity. The crater floor contains some of the oldest rocks in this region of Mars. The delta represents a younger period. The crater rim exposes even older terrain. This geological diversity meant Perseverance could study rocks from different time periods, piecing together Mars's environmental history. The rover itself, Perseverance, is a technological marvel. About the size of a small car, it weighs 2,260 pounds, 1,025 kilograms, and cost $2.7 billion to design, build, and launch. Its key features include wheels and mobility: 6 individually motorized wheels, each 20.7 inches, 52.5 centimeters in diameter, made of aluminum with titanium spokes. The wheels are deliberately damaged with treads that spell JPL in Morse code dots, and dashes that leave distinctive tracks, helping scientists study Martian soil. Cameras: 23 cameras in total, including Mast Cam Z, a pair of zoomable cameras on a mast 7 feet 2 meters above the ground, providing high-resolution color images and video. Supercam, a remote sensing instrument that can analyze rocks from up to 23 feet 7 meters away using lasers. Watson, a camera on the robotic arm for extreme close-ups. PIXL and Sherlock, X-ray and ultraviolet instruments for studying rock composition and detecting organic compounds. Robotic arm, a 7-foot 2.1-meter arm with instruments at its end for examining rocks up close. Sample collection. This is Perseverance's unique capability. The rover carries 43 sample tubes made of ultra-pure titanium. When scientists find an interesting rock, Perseverance can 1. Abrade, grind a small patch to remove weathered surface material. 2. Use PIXL and Sherlock to analyze the fresh surface. 3. If the rock looks promising, drill a core sample about the size and shape of a piece of classroom chalk. 4. Seal the sample in one of the titanium tubes. 5. Store the tube in the rover's belly for potential future return to Earth power. Unlike earlier rovers powered by solar panels, Perseverance uses a multi-mission radioisotope thermoelectric generator (MRTG), essentially a nuclear battery. It contains 10.6 pounds (4.8 kilograms) of plutonium-238, which generates heat as it decays. Thermocouples convert that heat into electricity, providing about 110 watts of continuous power, regardless of dust storms or Martian winter. This power system means Perseverance can operate for years, possibly decades, limited only by mechanical wear rather than energy availability. Chapter 3: The First Year Setting the Stage. First year on Mars was about exploration and understanding. The rover needed to traverse from its landing site on the crater floor to the delta, journey of about 1.6 miles, 2.6 kilometers that would take months. The crater floor campaign. Initially, scientists focused on understanding the crater floor itself. They quickly discovered something unexpected. Instead of sedimentary rocks deposited by the ancient lake, the crater floor consisted of igneous rocks formed from cooled magma, or lava. This was surprising but scientifically valuable. The igneous rocks told a story. After the impact created Jezero Crater about 3.9 billion years ago, volcanic activity filled parts of the crater with lava. Much later, water arrived and filled the crater, creating the lake. The igneous rocks on the crater floor represented the ancient volcanic activity, while the delta represented the later lake period. One formation on the crater floor, informally named Sita A, Navajo word meaning amidst the sand, contained olivine-rich rocks with large crystals. Large crystals form when magma cools very slowly, suggesting these rocks formed deep underground in a thick magma chamber. Later, erosion exposed them at the surface. Scientists also found something else. These ancient volcanic rocks showed signs of interaction with water. Carbonate minerals which form when carbon dioxide dissolves in water-filled cracks in the rocks. This meant that even the oldest rocks on Jezero's floor had been altered by water at some point. Moving to the delta in March 2022, Perseverance began its trek to the delta. The journey required careful navigation around hazards like sharp rocks and sand traps that could immobilize the rover. Using its autonomous driving system, Perseverance could analyze terrain ahead, identify hazards, and plan safe routes, sometimes covering more than 1,000 feet, 300 meters in a single Martian day called a sol. By April 2022, Perseverance reached the delta's edge. Scientists named this region the Bright Angel Formation. After the Bright Angel Trail in the Grand Canyon, many Martian features are named after geological formations on Earth. The delta immediately revealed itself as geologically rich. Orbital images had shown layered rocks, but up close, Perseverance could see the layers in stunning detail. These weren't just layers, they were pages in a history book written in stone. Understanding delta formation. Deltas form when rivers carrying sediments enter slower moving or standing water. The water velocity drops suddenly, and the sediments settle out. Coarser particles, sand and gravel, drop first, near the river mouth. Finer particles, silt and clay, travel farther into the lake before settling. Over time, as the river deposits more sediment, the delta builds outward. Layers accumulate, with each layer representing a snapshot of environmental conditions at that time. Geologists can read these layers like tree rings, understanding how the environment changed. Jezero's delta showed clear evidence of multiple episodes of sediment deposition. Some layers contained fine-grained mudstones, suggesting calm, steady water flow. Other layers contained larger rocks and boulders, suggesting occasional flash floods that swept material from highlands tens of miles away. This variable pattern told scientists snapshot of environmental conditions at that time. Geologists can read these layers like tree rings, understanding how the environment changed. Jezero's delta showed clear evidence of multiple episodes of sediment deposition. Some layers contained fine-grained mudstones, suggesting calm, steady water flow. Other layers contained larger rocks and boulders, suggesting occasional flash floods that swept material from highlands tens of miles away. This variable pattern told scientists that Mars's ancient climate wasn't uniformly wet. There were wet periods and dry periods, possibly controlled by orbital changes similar to how Earth's ice ages are influenced by orbital variations. The sample collection strategy. By September 2022, Perseverance had collected samples from both the crater floor and the delta. The samples showed remarkable diversity. Igneous rocks from the crater floor, providing a baseline for Mars's ancient volcanic history. Fine-grained mudstone from the delta, perfect for preserving organic material, if it existed. Rocks rich in sulfates, minerals that form from evaporating water, rocks containing carbonates, even a sample of Martian atmosphere. Each sample was meticulously documented with hundreds of images and detailed compositional analysis. Scientists gave each sample location informal names, often inspired by national parks on Earth: Rochette, Cid Montanier, Wildcat Ridge, and dozens more. 1 sample in particular caught scientists' attention. Collected in September 2022 from a location called Wildcat Ridge, this rock contained abundant organic molecules, carbon-based compounds that on Earth are associated with life. The rock also contained sulfate minerals, suggesting it formed in a lake that was slowly evaporating. The presence of organic molecules didn't prove life existed. Organic molecules can form through non-biological processes, but it showed that Mars once had the chemical ingredients necessary for life. By mid-2024, Perseverance had collected more than 20 samples and was exploring a new region of the delta. Scientists were optimistic but cautious. They had found promising signs: organic molecules, evidence of long-lived water, minerals that formed in habitable conditions, but nothing definitive. That was about to change. Part 2. The Discovery. Chapter 4. July 2024. An unexpected find on July 18, 2024. Perseverance was exploring an outcrop in the Bright Angel Formation along the northern edge of Naretva-Valasan, ancient river valley, about a quarter-mile 400 meters wide, that once fed water into Jezero Crater. The rover's cameras had spotted an interesting rock formation, and the science team decided it warranted closer inspection. They drove Perseverance alongside an arrowhead-shaped rock measuring about 3.2 feet by 2 feet 1 meter by 0.6 meters. The team gave it an informal name, Cheyava Falls, after the spectacular Cheyava Falls in the Grand Canyon, a 100-foot waterfall that flows through a remote canyon carved over millions of years. The name seemed fitting for a rock that might hold evidence of Mars's watery past. At first glance, Cheyava Falls looked intriguing but not extraordinary. It was reddish, like most Martian rocks, with visible layering suggesting it was sedimentary. White veins of calcium sulfate ran through it, clear evidence that water had once percolated through the rock, depositing minerals along cracks. But when Perseverance's Watson camera took close-up images, the science team saw something they'd never seen before on Mars. The rock was covered with distinctive spots, each a few millimeters across. The spots were irregularly shaped, light-colored at their centers, and ringed with dark material. They looked exactly like leopard spots. Initial analysis: the team immediately knew this was significant, but they needed to understand what they were looking at. Perseverance's sophisticated instruments began a detailed investigation. First, the Sherlock scanning habitable environments with Raman and luminescence for organics and chemicals. Instrument: a device that uses ultraviolet laser light to identify organic compounds and minerals, scanned the rock. The results were immediate and exciting. Organic molecules. The rock contained carbon-based compounds throughout its matrix. Next, Pixel planetary instrument for X-ray lithochemistry took over. Pixel bombards rocks with X-rays and analyses the spectrum of X-rays the rock emits back, determining its elemental composition with extremely high precision down to individual grains of material. Pixel's scans of the leopard spots revealed something remarkable. Each spot had a distinctive chemical composition. The light-colored centers contained high concentrations of iron and phosphorus, forming a mineral called vivianite hydrated iron phosphate. The dark rings surrounding each center contained iron and sulfur, forming a mineral called greigite iron sulfide. This combination vivianite cores surrounded by greigite halos formed a reaction front pattern that scientists recognized immediately. What reaction fronts tell us on Earth? These kinds of reaction fronts form when chemical reactions occur in sediment. Specifically, they form when microorganisms mediate chemical reactions, extracting energy by moving electrons between different compounds. Here's how it works. In waterlogged sediment with organic matter, bacteria that need oxygen but can't get it from the atmosphere or water will breathe other compounds instead. Some bacteria can pull oxygen from iron oxide rust, converting oxidized iron Fe cubed to reduced iron Fe squared. This process releases energy the bacteria use to survive. When this happens, in sediment rich in phosphorus, the reduced iron combines with phosphorus to form vivianite. The vivianite appears as blue-green nodules visible to the naked eye, though on Mars, radiation and other factors had turned it light-colored instead of blue-green. Similarly, other bacteria can reduce sulfate SO squared to sulfide S, gaining energy in the process. When sulfide encounters iron, it forms iron sulfide minerals like greigite. On Earth, greigite is almost exclusively associated with bacterial sulfate reduction in oxygen-poor environments. The leopard spot pattern vivianite centers with greigite halos suggested a specific sequence of chemical reactions, potentially mediated by microbial metabolism. The geology adds context. The rock's overall structure supported this interpretation. Cheyava Falls was a fine-grained mudstone mud that had compacted into rock. The fine-grained size suggested it formed in calm water conditions, possibly the bottom of Jezero's ancient lake. The calcium sulfate veins running through the rock proved water had moved through it after it formed, potentially providing energy and nutrients for microbial communities. The rock showed no evidence of having been heated to high temperatures. This was important because heat can drive similar chemical reactions without biology. If the rock had been baked by volcanic activity, the leopard spots might have formed abiotically, but there was no evidence of heating. Additional surprises as the team studied Cheyava Falls more intensively over the following days. They found other intriguing features. Olivine crystals. Small green crystals of olivine were scattered through the rock. Olivine is a mineral that forms in volcanic rocks, not sedimentary rocks. How did olivine end up in a sedimentary rock? There were two possibilities. Either volcanic ash fell into the ancient lake and mixed with the mud, or Martian wind later deposited olivine rich dust into cracks in the rock. Either way, this added complexity to the rock's history. Poppy seeds. In addition to the larger leopard spots, the rock contained numerous tiny dark spots that resembled poppy seeds. These were rich in iron and phosphorus, similar to the leopard spots but smaller and without the distinct ring structure. Layered structure. The rock showed subtle layering, suggesting it built up over time from repeated deposition of sediment, evidence of a long-lived, stable aquatic environment. Chapter 5. The debate begins within hours of seeing the first images. The Perseverance science team was engaged in intense discussion. The images and data were shared with collaborators around the world, hundreds of scientists specializing in geology, geochemistry, biology, planetary science, and astrobiology. The central question: could these features have formed without biology? The case for biology. Several factors supported a biological interpretation. 1. The mineralogy. The vivianite-greigite combination is, on Earth, strongly associated with microbial activity. Lab experiments have shown that greigite only forms in the presence of live bacteria when sulfitrators in microbes are actively metabolizing to the pattern. The concentric ring structure vivianite cores surrounded by greigite halos matches the pattern of bacterial reaction fronts in Earth's sediments. 3. The context: fine-grained mudstone deposited in a lake is exactly the kind of environment where life thrives on Earth. The presence of organic molecules, phosphorus, and sulfur provides the necessary ingredients. 4. The preservation: the rocks showed no signs of heating or severe alteration that might destroy biosignatures or create abiotic mimics. Dr. Joel Hurowitz, the lead author of the study that would eventually be published about Cheyava Falls, explained, "The combination of chemical compounds we found in the Bright Angel formation could have been a rich source of energy for microbial metabolisms." Dr. Sunanda Sharma, a perseverant scientist studying reaction fronts, noted, "On Earth, these types of features in rocks are often associated with the fossilized record of microbes living in the subsurface. The case against, or at least for caution science, demands skepticism, especially for extraordinary claims." Several scientists urged caution. 1. The olivine problem. Olivine forms at high temperatures, typically above 1200 degrees Celsius. If olivine formed in this rock while it was hot, that heat might have driven the chemical reactions that created the leopard spots no biology required. However, detailed analysis suggested the olivine was likely added later, after the rock formed and cooled. 2. Unknown Martian chemistry. Mars is a different world with different chemistry. Could unknown abiotic processes unique to Mars create similar patterns? It's hard to prove a negative. 3. The ambiguity of organic molecules. Organic molecules can form without life. They're found in meteorites, interstellar dust clouds, and can be produced by volcanic activity or impact events. 4. Confirmation bias. Scientists are human. After years of searching for life on Mars, there's a risk of seeing what we want to see. Extraordinary claims require extraordinary evidence. Dr. Katie Stack Morgan, Perseverance's project scientist, emphasized this point. Astrobiological claims, particularly those related to the potential discovery of past extraterrestrial life, require extraordinary evidence. The peer review process: the team knew their findings needed rigorous scrutiny. They spent months analyzing the data, considering alternative explanations, and debating interpretations. Other teams were invited to examine the data independently. They consulted with experts in microbiology and microbial ecology, geochemistry and mineralogy, sedimentology, and stratigraphy, organic geochemistry, planetary geology, astrobiology, and biosignature detection. The team wrote a detailed scientific paper describing their findings, methods, and interpretations. This paper underwent peer review process, where other experts in the field anonymously evaluate the work for scientific rigor, methodology, and conclusions. Peer reviewers asked tough questions. Had they considered all possible abiotic explanations? Were their analytical methods sound? Did their interpretations overreach their data? What were the uncertainties and error bars? What additional tests would strengthen or weaken their conclusions? The review process took months. The team revised their paper multiple times, addressing reviewer concerns, adding analyses, and tempering some interpretations.